Hello, this is Professor Kitch. Welcome to this webcast from my Introduction to Geotechnical Engineering course. This is the second of two webcasts on the three phases of soil and how to solve weight-volume problems. In the previous webcast on solving weight-volume problems, we covered how to solve problems when you are given specific quantities about the soil, such as total volume and total weight. We call these Type 1 problems. In this webcast, we will solve Type 2 problems. These are problems where the input or given information is in relative quantities, such as water content, void ratio, or unit weight. The principles are the same as presented in our previous webcast, but the solution technique is slightly different. In this example, we're given a sample of clay which is saturated and has a water content of 48%. We also know that the specific gravity of the solids is 2.73. What we want to find are the void ratio, porosity, and unit weight in both SI and English units. The solution starts, as always, with drawing a three-phase diagram. Here's the first secret or key to solving this problem. Use a phase diagram with the mass in grams on the left-hand side and the volume in cubic centimeters on the right. This is different than the problems we solved earlier, where we used weight in pounds or kilonewtons and volume in cubic feet or cubic meters. You don't have to use grams and cubic centimeters for this problem, but it makes the math much easier if you do. You'll see, just pay attention. Now, in our problem, the soil is saturated, so we already know that the volume of air is 0, so we can write that in the diagram. However, we don't know any other specific quantities in the diagram. So how do we get started on this problem? Well, here's secret number 2. Guess one of the values and figure the rest out from there. Now we can guess almost any one of these values, but if we guess that the mass of the solids is 1 gram, the problem will be easier than if we make any other guess. So we'll write 1 in for the mass of the solids. From a definition of water content, we can write that the mass of water is equal to the mass of solids times the water content in decimal form. This is equal to 1 gram times 0.48 or 0.48 grams. Do you see now why we chose the mass of the solids to be equal to 1 gram? I don't know about you, but next to 0, 1 is my favorite number. I like multiplying by 1. I don't even need my calculator for that. So we enter 0.48 in the diagram for the mass of water. The total mass then is 1 plus 0.48 or 1.48 grams, and we enter this in the diagram. Now we're ready to move from the mass side of the diagram to the volume side of the diagram. When we did this last time, we used the unit weight gamma to compute volumes from weights. However, this time we have mass instead of weight, so we will be using density rho to get from mass to volume. We'll start with the water. The volume of water will be the mass of water divided by the density of water. Now you'll see the value of secret number 1 using the units of grams and cubic centimeters. Do you recall the density of water in grams per cubic centimeter? This is a value you should know, and it's easy. My second favorite number, 1 gram per cubic centimeter. So the volume of water is 0.48 grams divided by 1 gram per cubic centimeter, or 0.48 cubic centimeters. I love dividing by 1, even more than multiplying by 1. Let's put that value in the diagram. We'll use the same process to determine the volume of the solids. The volume of the solids is the mass of the solids divided by the density of the solids. This is the mass of the solids divided by the quantity, the specific gravity of the solids times the density of water. Remember that the specific gravity relates the density of a material to the density of water. This is equal to 1 gram divided by the quantity 2.73 times 1 gram per cubic centimeter. I will need my calculator to compute this, and it comes out to 0.366 cubic centimeters. We'll write that on the diagram. Next, we'll compute the total volume as 0.366 plus 0.48, or 0.846 cubic centimeters, and put that on the diagram. And finally, since the soil is saturated, the volume of the voids will be equal to the volume of the water, 0.48 cubic centimeters. We'll enter that to complete the three-phase diagram. So here's our completed three-phase diagram for this saturated soil. All that's left to do is to solve for the void ratio, porosity, and unit weights. We'll start with the void ratio E, which is defined as the volume of voids over the volume of solids, or 1.48 divided by 3.66, which is 1.31. Remember, the void ratio is always presented in decimal form, so we don't multiply by 100%. This is an interesting value. The void ratio is greater than 1, which tells us the soil has more void space than solid space. This is not unusual for saturated soft to medium clays. They can have a large capacity to absorb and hold on to water. We'll discuss this phenomenon more in section 4.5 of the text when we discuss clay mineralogy. The porosity N is equal to the volume of voids divided by the total volume, or 0.48 divided by 0.846 times 100%, which is 56.7%. Again, more void volume than solid volume. To calculate the unit weights, we need to calculate the densities and then convert those densities to unit weight. The total density rho is the total mass divided by the total volume, or 1.48 grams divided by 0.846 cubic centimeters, which is 1.749 grams per cubic centimeter. The dry density, rho sub d, is the mass of the solids divided by the total volume, or 1 over 0.486, which is 1.182 grams per cubic centimeter. Now we have to convert these densities to unit weights. To do this, we'll recall that the density of water is 1 gram per cubic centimeter, and the unit weight of water is 62.4 pounds per cubic foot, or 9.81 kilonewtons per cubic meter. These are quantities which you should commit to memory. To get the unit weight gamma, we simply multiply the density we computed by the unit weight of water and divide by the density of water. Since we're multiplying by the same property of water on the top and the bottom, this will simply change the units of our previous calculation from density to unit weight. So, the total unit weight will be 1.749 grams per cubic centimeter divided by 1 gram per cubic centimeter times 62.4 pounds per cubic foot, which gives us a total unit weight of 109.1 pounds per cubic foot. In SI units, the total unit weight will be 1.749 grams per cubic centimeter divided by 1 gram per cubic centimeter times 9.81 kilonewtons per cubic meter, or 17.1 kilograms per cubic meter. The dry unit weight will be 1.182 grams per cubic centimeter divided by 1 gram per cubic centimeter times 62.4 pounds per cubic foot, or 73.7 pounds per cubic foot, or 1.18 grams per cubic meter divided by 1 gram per cubic centimeter times 9.81 kilonewtons per cubic meter, or 11.6 kilonewtons per cubic meter. So let's review the key concepts we use to solve this problem. First, we use the units of grams and cubic centimeters in a three-phase diagram. Second, we started by assuming we had 1 gram of solid material. Third, we solved for density first, rho, and then converted density to unit weight, gamma, at the end. And finally, you need to memorize the density and unit weights of water in the various units. Let's try a second, slightly different example. In this example, we're conducting a laboratory compaction test. Our lab sample has a total unit weight of 19.5 kilonewtons per cubic meter. Its moisture content is 17%, and the specific gravity of the solids is 2.70. We want to know the dry unit weight, porosity, void ratio, and degree of saturation. As always, we will start with a three-phase diagram. This time, however, we'll use the units of kilonewtons for weight on the left and cubic meters for volume on the right. We choose these units because we already know the total weight in kilonewtons per cubic meter. We'll start off again by assuming the amount of solid material. In this case, the weight of the solids will be 1 kilonewton. The weight of water will then be the weight of solids times the water content, or 1 times 0.17, which gives us 0.17 kilonewtons of water, and we enter that on the diagram. And then we add the weight of solids and water to compute the total weight as 1.17 kilonewtons, which we enter on the diagram. Moving to the volume side, we start with the water and compute the volume of water as a weight of water divided by the unit weight of water, which is 0.17 kilonewtons divided by 9.81 kilonewtons per cubic meter. That gives us a volume of water of 0.0143 cubic meters, which we enter onto the diagram. The volume of solids is computed as the weight of solids divided by the unit weight of solids. This is the weight of solids divided by the quantity, the specific gravity of solids, times the unit weight of water, or 1 kilonewton divided by 2.7 times 9.81 kilonewtons per cubic meter. This comes out to be 0.0378 cubic meters, and we'll enter that on the diagram. Now, to determine the total volume, we'll have to use the information we have about the total unit weight of our soil. By definition, we know that the unit weight of soil is the total weight divided by the total volume. We can rearrange this equation to show that the total volume is the total weight divided by the unit weight. Using this equation, we can compute the total volume as 1.17 kilonewtons divided by 19.5 kilonewtons per cubic meter, which is 0.06 cubic meters. We enter this on the phase diagram, and then we compute the volume of air as 0.06 minus 0.143 minus 0.0378. This gives us a volume of air equal to 0.0079 cubic meters, and we enter that onto the diagram. To complete the three-phase diagram, we compute the volume of voids as 0.0143 plus 0.0079, which is 0.0222, and we enter that on the diagram. Now the hard part is over. All we need to do is compute the quantities we're interested in. The dry unit weight is the weight of the solids divided by the total volume, or 1 divided by 0.060, which is 16.7 kilonewtons per cubic meter. The void ratio is the volume of voids divided by the volume of solids, or 0.222 divided by 0.0378, which is 0.587. The porosity is the volume of voids divided by the total volume, or 0.0222 divided by 0.0600 times 100%, which is 37.0%. Finally, the degree of saturation is the volume of water divided by the volume of the voids, which is 0.0143 divided by 0.0222 times 100%, which is 64.4%. And we're done. I hope this webcast helps you to solve weight volume problems when you've given relative quantities as the input to the problem. I've showed you a couple tricks to make solving the problems easier and faster. But the key thing to remember is always to draw a complete three-phase diagram. This is Professor Kitch, hoping you have a great geotech day.